Everybody, welcome back to another video. In this video, we are going to be talking about antiderivatives and the rules of integration. So, antiderivatives and rules of integration. Well, antiderivative probably means we're going to try and undo derivatives somehow. That's a pretty natural question to ask after the first half of a calculus course is, okay, well, we've been spending all this time taking derivatives, but is it possible for me to undo them? For instance, if I give you a function and I say, oh, this function is the derivative of something else, is it possible to get back to something else? And the answer to that is going to be kind of, right? Not entirely. For instance, let's say we had some function that is differentiable. Right? So we have some function capital F of x. Well then, the derivative of capital F of x will be f prime of x, but that's not the only function with derivative f prime of x. Also, derivative with respect to x of f of x minus 3. Derivative of a constant is 0, so this will still just be f prime of x. And the same would be true for any constant that I would choose to add or subtract here. So if you just handed me f prime of x, I can't necessarily give you back f of x, but I can give you back f of x plus something. Right? I know it'll be f of x up to possibly the addition of a scalar constant. So, let us make that kind of more formal. A function capital F of x is an antiderivative of little f of x on an interval I. That interval could be all real numbers, often it is in this class, but doesn't have to be. So, f of x is an antiderivative of little f of x on an interval I if capital F prime of x is equal to little f of x for all x in the interval. So basically, if you can find some function such that when you take the derivative of that function, you get back your original one, then you say, oh, that big function, capital F of x, is an antiderivative because it has as its derivative your target. Alright, so let's do an example. Let's show that capital F of x equal to x to the 7th plus 1/5 x to the 5th minus 4x plus 1 and g of x equal to x to the 7th plus 1/5 x to the 5th minus 4x minus 2 are antiderivatives of little f of x equal to 7x to the 6th plus x to the 4th minus 4. Alright, so how do we show that functions are antiderivatives of another function? Well, let's take the derivative of those and see if we get back what we're going for. So our proof of that, capital F prime of x by the power rule, by the sum rule, 7x to the 6th plus 5 times 1/5 is 1. So we're going to have 1x to the 4th. Derivative of minus 4x will be minus 4. And derivative of plus 1 is 0. So 7x to the 6th plus x to the 4th minus 4 matches with our little f of x. So, check. Capital F is an antiderivative. How about capital G prime? Well, 7x to the 6th plus 5 times 1/5 is 1, x to the 4th. Minus 4x, derivative of that is minus 4. And then the derivative of minus 2 is 0 again. So this is it, and we'll have that be equal to f of x again. Alright, and that's all there is to it. F and G are therefore both antiderivatives of little f of x. So that's an important thing to kind of get, is antiderivatives are not unique, because I can add any constant on and it doesn't change the derivative. Alright, so you might ask the question, are those the only antiderivatives? Like if I have one antiderivative, does that mean that all the other antiderivatives are just that first one plus some constant? And the answer is yes. Which is a very nice answer, because otherwise it'd be hard to find them. Now it means you only have to find one. So, let capital G of x be any antiderivative of little f of x on an interval I, then every antiderivative capital F of x on I has the form capital F of x is going to be equal to G of x, possibly plus some constant, where C is a real number. And we typically write this with a capital C, and we'll discuss that in a bit. Alright, so that's very nice. It tells you, hey, once you have one antiderivative, you essentially have all of them. Just put on an extra arbitrary constant at the end. Okay, so let's move forward and kind of see an example of what that means pictorially. Let's say little f of x is 1. Well, the clear antiderivative of this one would be just x. So G of x equal to x is an antiderivative of little f of x, technically on R, because this is going to be true for all real numbers. If it's on R, we typically just don't specify the interval. So this is because G prime of x is equal to 1, which is, of course, f of x. but so is capital F of x equal to x plus 2. Or capital H of x equal to x minus 4. These are also antiderivatives of function. In fact, any plus c is an antiderivative, right? This is just plus negative 4. So these are precisely the antiderivatives, and if you graph them all, you say, okay, g of x equal to x, that would look like that. Great, so why is this have its derivative as 1? It's because it's a line with slope 1, or would be if I could draw straight lines. Okay, but what about f of x? Maybe if I say that's 2. Capital F of x looks like this. So because the derivative only cares about the slope and not about where you are vertically, we see, oh, this is also going to be the same kind of thing, right? It's also an antiderivative, for 1. Ditto down here if we said this was negative 4, have something that looks like that. So that would be capital F of x up there, that would be capital H of x down there, and both would be antiderivatives of 1 as well. And you can visually see anywhere you shifted these lines up and down, you would get an antiderivative, right? So maybe there's one right in there. In fact, there is one right in there. So on and so forth. So how do you get antiderivatives? Like, we've just supplied ones and we've been able to check that things are antiderivatives. How do you actually get to them? Unfortunately, that process is a little bit more complicated, but fortunately, we're going to spend a few weeks learning how to do it. So you will all be experts by the time we are done with this class. Alright, the process of finding all antiderivatives, right? As soon as you find one, you find all of them. So the process of finding all antiderivatives of little f of x is called, as you might have guessed, anti-differentiation. But it has another more common name, which is integration. And just like we had the symbol ddx to denote take a derivative, the symbol of this operation is denoted kind of a tall squiggly S thing. And it is known, this is known as an integral sign. Alright, and I'm going to make one more definition real fast, and then we'll start talking through all of these. So what we'd say is integral of f of x, and then what we do is we put a little dx there, I'll discuss that in a second, is equal to capital F of x plus c. If this is true, this tells us that the indefinite integral is not going to be just one function, it's going to be all possible antiderivatives. And it'll be the family capital F of x plus c, where c is just some arbitrary real number or complex number. Okay, so let's talk through all these definitions since there's a lot here. We're anti-differentiating, we're integrating, we're finding the opposite of a derivative. And we're going to denote that with this integral sign, right? So what are all these extra pieces, parts that are floating around? Why is that the symbol? I said that this symbol is kind of made to look like an S. We'll see in a couple sections something called a definite integral. This is an indefinite integral. Soon we'll see the definite integral, which actually came first. And the definite integral came from like a limiting process of summing up a bunch of things. We'll discuss that when we get there. But basically they were like sum S, but stretch it out. And then we got the integral sign. So you can blame Newton and Leibniz for that. But yeah, so this is the indefinite integral. Not just a single function, but the entire family of things, such that when you take the derivative of this side, you get back little f of x. We have special names for the f of x and the c. We call little f the integrand, and it's f of x, right? Technically the name is just f, but f of x. That's the integrand, the thing you're integrating. And we call c a constant of integration. Your indefinite integrals must always have a plus c at the end, because you're finding a family of solutions, not just a single one. So, most common calculus mistake, missing a plus c. Happens to us all. It'll happen probably to every single one of you, and to me. But yeah, please try to keep it in there as much as possible. Okay, and so why, the only kind of confusing part for that is left is probably this little dx thing. Why the heck is that there? Well, the dx is going to remind us what variable we're integrating with respect with. In other words, it denotes our independent variable. And you might say, that's stupid. Why isn't it always just x? Like, why are we bothering to write that? Well, maybe I have a function of a different letter. Maybe I have a function of t. I could write integral of f of t dt, right? And because I have a t as my independent variable here, I want to be integrating with respect to t, because that's kind of the important letter in this thing. And you might still say, okay, but it should still be pretty obvious to you that you're working with that letter. Sure, I'll give you that in the single variable case. However, single variable calculus is not the only calculus there is. In multivariable calculus, it's very common to have a function of multiple variables. So for instance, you have a function of x and y, and then you'd say, okay, I want to integrate it first with respect to x, and then I want to integrate it again with respect to y. And hopefully by the end of this course, I'll have demonstrated some of the reasons why you would want to do this, even though we won't be doing it here. But yeah, so it's possible to do this sequentially. And then knowing which variable you're integrating with respect to at which time is important, because this would most of the time, or that's exactly what I wrote the first time, would not be the same as this. So swapping those is not a commutative operation in general. My general point is you're going to want to write this down to keep track of it because it's good practice, good habit, and it's really the only correct thing to do. Alright, so let's start by computing some indefinite integrals. Based off of the two examples we saw earlier about antiderivatives, we know that, for instance, the integral of 1 with respect to x is x plus c. So that was by the example we did previously. And then that very first example we did with the x to the 7th thing, that tells us that the integral of 7x to the 6th plus x to the 4th minus 4 dx will be equal to x to the 7th plus 1/5 x to the 5th minus 4x plus c. Alright, so that's all well and good, right? We found those ones, but this was, again, because we started here, took a derivative, and got back this. Is there any way where I can just start with some function and get to here without already kind of knowing the answer? Sort of. In some sense, you always will know the answer beforehand. In other senses, no, you definitely won't, and there are ways to get to it. Now, in order to do that, let's start talking about some of the rules of integration. Just like differentiation has rules, integration has rules that make it nice and simple to work with. Because in general, it's hard to find an antiderivative. If you just try to brute force it, there's infinitely many functions out there. Okay, so integration rules. Where do we go from here? Well, first let's talk about the indefinite integral of any constant. Oftentimes you'll hear me drop the word indefinite and I'll just say the integral of this. So technically that's me being sloppy, but it will happen. I just force habit. Okay, so the integral of any constant k dx is kx plus c. And this is true for all real numbers or complex numbers. Okay. Okay? Prove it. Fine. I'm going to take the derivative of that right side. And lo and behold, that drops to 0, and that'll just give me k. Rule proved. So really, we define integrals as this inverse to differentiation. How do you prove an integral rule? You take the derivative of what it is, right? You make an educated guess, you take the derivative, and if it works, it works. And then what we'll be able to do is we'll be able to piece together smaller integrals to make bigger and better. So let's evaluate a couple integrals. So integrate 4 with respect to x, and pi squared minus 1 dt. so take a 10 seconds to think about those. Don't hurt yourself. All right. The integral of 4 with respect to x, according to our rule, 4 is just taking the place of k. So it'll be 4x plus c. The integral of pi squared minus 1 dt. Pi squared minus 1, complicated number, but still just a number. So this will be pi squared minus 1 times. Now, our independent variable, instead of being x, is t. So it'll just be pi squared minus 1 t plus c. Alright, now let's try to undo another differentiation rule. Here we've undone the constant rule. Now let's try to undo the power rule. And we'll recall that the derivative with respect to x of x to the nth power is n times x to the n minus first power. 1 second, I'm getting a call. Never mind, spam call from Minnesota. How about that? Okay, so derivative of x to the n is n times x to the n minus 1, and this is true except in one particular case. N can't be 0, right? When n is 0, then this would be a constant and the derivative of the constant 0. I guess you could still get away with saying that, even in this case. Yeah, let's leave it. Alright, so what does this tell us? This tells us that we have a power rule for integration. If I just start with x to the n minus 1, I'd have to divide over there, right, in order to integrate, but I'd get back x to the n. So, the integral of x to the nth power, dx, will be 1 divided by n plus 1 times x to the n plus, words, x to the n plus first power plus c. And this is true as long as n is not equal to negative 1. Why can't n be equal to negative 1? Well, if I plug negative 1 into this formula, I can divide by 0 error, so that'd be bad. Alright, let's prove this formula. And again, we're going to prove it by taking the derivative of this side over here. d dx of 1 over n plus 1, x to the n plus 1 plus c. Plus c will drop, and you'll have n plus 1 divided by n plus 1 times x to the nth power. That's 1, so this is just x to the n as desired. Alright, so we have this power rule as long as n is not equal to negative 1. We'll handle that case in a minute. Alright, but first, a couple examples. Let's evaluate the integral of x to the 4th power dx, the integral of x to the 5/3 power dx, and the integral of 1 over x squared dx. Alright, and all of these just get handled by the power rule. The integral of x to the 4th dx, okay, clear power rule. In this case, n is equal to 4. So by our formula, we would get 1 over 4 plus 1 x to the 4 plus first power plus c. In other words, 1/5 x to the 5th plus c. Alright, nothing too fancy going on. Let's try this next one. Integral of x to the 5/3 dx will be 1 divided by 5/3 plus 1. Doesn't matter whether n is an integer or not. It just has to be any number. Always, you'll add 1, divide by it, and it'll be times x to the 5/3 plus 1 plus c. Run that through. 5/3 plus 1 is 5/3 plus 3/3, aka 8/3. 1 over 8/3 is 3/8. And this will be x to the 8/3 plus c. And now you can see for yourself a specific example of where the power rule makes sense. Because if I were to take the derivative of this, I'd say, oh, 8/3 times 3/8 cancels out. I'm going to get the 1 coefficient from here. 8/3 minus 1 is also 5/3. Alright, let's try that last example. The integral of 1 over x squared dx, well, that doesn't necessarily look like a power rule to start, but if we rewrite using our rules of exponents, this is the integral of x to the -2nd dx. Now the power rule says this is 1 divided by -2 plus 1 times x to the -2 plus 1 plus c. Or in other words, -2 plus 1 is -1, so we'll be left with negative x to the -1st, aka -1 over x plus c. So, not too complicated. Power rule, pretty simple, pretty straightforward since it's just undoing power for differentiation. Okay, couple of quality of life rules. Scalar multiples, pull out of integrals, just like we did for derivatives. The integral of little c times f of x, heck, let's make it k so we don't confuse it with that c. Integral of little k times f of x dx is k times the integral of f of x dx, and this is true for all k and r. Okay, and then we also have a sum rule for integrals, which says that if you have two integrable functions, that the integral of f of x plus g of x dx is the integral of f of x dx plus the integral of g of x dx. And this is true for subtraction as well. To prove these, you apply the corresponding rules of differentiation on each of those sides, and it all works out very nicely. Sweet. So, scalar multiples, sum rule, just ease of life, quality of life update. Okay, next page. We can use this to evaluate the integral of almost all rational functions already. And we'll handle the last little bits to get all of them in just a second. Here it is. Alright. Let's evaluate the integral of -3x to the -2nd plus 7x minus 4 dx, the integral of 4t squared plus b times t dt and the integral of 3a plus 4x dx, where a and b are just constants. Okay, this won't be too bad. Let's do the first one first. Integral of negative 3x to the negative second plus 7x minus 4 dx. Well, I see the sum of three things together. Let's use the sum rule to split all those up. That will be the integral of negative 3x to the negative second dx plus the integral of 7x dx minus the integral of 4 dx. Okay, well, that one we already know how to do. That one's a constant. I see some scalar multiples on those. Let's just pull those out. Field negative 3 times the integral of x to the negative second dx plus 7 times the integral of x dx minus the integral of 4 dx. Alright, and now the power rule says you can just straight up evaluate all those. Oh, power rule's going to point to some rule now. Power rule says, hey, you know how to evaluate all those. You should do this on your own to make sure that you're getting it, but it should give you negative 3 times negative 1, so negative x to the negative first, plus 7 times 1/2 x squared minus 4x plus c. All right. So I want to point out two things there. These are the power rule, and then this is the constant rule. Simplifying. Just gives us negative 3 times negative 1 is positive 3. So we'll have 3x to the negative first plus 7/2 x squared minus 4x plus c. You might be asking, why is there only 1 plus c? Like, shouldn't I have had a plus c here, and here, and here? Technically, yes. Now, here's why we can get away without writing all of that. It's just a constant. Some unknown constant, right? Plus c. Negative 3 times a constant is just another constant. Add on 7/2 times that constant, add on 7 times that constant, it's still just another unknown constant. Subtract away another constant, still just another constant, right? It's all one big constant. So why bother writing around a bunch of like different plus c's? We're just going to put the 1 at the end, and that takes care of all of it, and would still hold true. Because if you took the derivative of this, you would still get back that. So that's nice. Alright, let's do that second integral. The integral of 4t squared plus b times t dt. Okay, applying the sum rule and the scalar rule gives you, this is 4 times the integral of t squared dt plus b times the integral of t dt. Okay. Why is the b pulled out? Because the b is just another constant. We don't know what it is. Fine. It still pulls out of the integral sign because that's just how integrals work. They say, well, it doesn't matter what your constant is. It just pulls out no matter what your function and no matter what your constant are. The only thing you really can't pull out from an integral is the variable you're actually integrating, right? Like I can't pull an x out from, well, not from that. I couldn't pull an x out from here, or I couldn't pull this t squared out, right? Because those are not constants, with respect to our variable of integration. So those actually have to be dealt with. Thankfully, these ones get dealt with by the power rule. That'll give you 4 times 1/3 t cubed plus b times 1/2 t squared, all plus c at the end. So you get 4/3 t cubed plus b divided by 2 t squared plus c. Nice and simple. Let's try the last one. Same kind of idea for it. The integral of 3a plus 4x dx. Well, that's the integral of 3a dx plus 4 times the integral of x dx. This is just a constant. Again, unknown constant. Doesn't matter. It's still just going to be 3a times x, because that's what the constant rule says. Integral of x is 1/2 x squared, so this will be plus 4 times 1/2 x squared, all plus c. Rewriting, that'll be 2x squared plus 3ax plus c. Just swapping around the order of those two there. Alright, I think that's enough examples for the sum rule and the power rule, all that jazz. Let's talk about exponential derivatives and integrals, and then logarithmic derivatives and integrals. Or rather, we've talked about the derivatives, let's talk about their integrals. Alright, well, the derivative of an exponential function is an exponential function, so it would make sense for the integral to do the same thing. The integral of e to the x dx is equal to e to the x plus c. And our proof? The derivative of e to the x plus c is just, well, that drops, and we're going to be left with e to the x. Nice and simple. We will deal with the case a to the x a little bit differently. We haven't really done the chain rule for integration yet. We'll handle that, but at a later date. It's slightly more complicated. Now, we have one other special case for integration that we're going to talk about right now. The integral of 1 over x. Right? We had the power rule, which said integral of x to the n dx is equal to 1 over n plus 1, x to the n plus 1 plus c. And this was true for n not equal to -1. So here's that missing case. Okay, the integral of 1 over x dx is going to be equal to the natural log of the absolute value of x plus c. And it's true for all x not equal to 0. Why is that? Because the derivative of the natural log of the absolute value of x from our last video is 1 over x. So if we integrate 1 over x, it breaks the pattern for the power rule and gives us natural log of x. Let's do a couple examples. Then we'll have one more topic to talk about, and then that'll be it. Let's evaluate the integral of 3x squared minus 4e to the x plus 2 over x dx, and the integral of e to the x minus 3 over x dx. All right. First integral. Let's apply the sum rule and the scalar rules. This is 3 times the integral of x squared dx minus 4 times the integral of e to the x dx plus 2 times the integral of 1 divided by x dx. Let's also just recall this is equal to x and negative first for convenience. Okay. Power rule says, oh, this is 3 times x cubed divided by 3, or let's write it in the same form. 1/3 x cubed minus 4 times the integral of e to the x is e to the x plus c, plus 2 times the natural log of the absolute value of x. And then it all has that 1 giant plus c at the end. Simplifying, that gives you x cubed minus 4e to the x plus 2 natural log of the absolute value of x plus c. So again, even though coming up with these rules is not necessarily the nicest thing in the world, once you have them, integrals tend to be pretty straightforward. At least so far. They're kind of like puzzles, where it's like you gotta figure out what rule to apply where. And sometimes that's not as complicated, sometimes it is. But we'll deal with those when the time comes, as the saying goes. Let's do that second one. The integral of e to the x minus 3 over x dx is the integral of e to the x dx minus 3 times the integral of 1 over x dx, which will be e to the x minus 3 natural log of the absolute value of x, all plus c. Alright, that's it for those 2 examples. Now let's talk about the one kind of large topic for this, right? Because integrals, cool. Like, I guess. You can undo derivatives. Woo! Why do I care? 2 reasons. One of them will come in 2 sections later when we talk about definite integral, and that has countless real-world applications. And the other one has perhaps even more real-world applications. And we're going to talk about it right now. It's known as differential equations. What is a differential equation? A differential equation is an equation, surprise, surprise, that involves a function and its derivatives. First derivatives, second derivatives, nth derivatives, doesn't matter. One of the most classic examples would be something like f double prime of x plus f of x is equal to 0. So in other words, the second derivative of f plus the original function gives you 0. It's a very classic problem. For those of you who know some trigonometry, it turns out that the two linearly independent solutions to that are sine and cosine. All right. So on to kind of I'm starting that sentence over. On to differential equations that we're going to actually deal with here. Any function that satisfies this is going to be a solution. So it doesn't matter. Differential equations can have more than one solution. Oftentimes they do. Sometimes they have infinitely many. In fact, most of the time they have infinitely many. But yeah. So let's do a differential equation. Let's solve f prime of x is equal to 3x minus 7. But I know how to solve these ones. If I just have a single derivative, we can solve those very quickly by integrating. Why? Well, f of x is an antiderivative of f prime of x. By definition, right? F prime of x is the derivative of f of x. So, f of x is equal to the integral of f prime of x dx, which is equal to the integral of 3x minus 7 dx. Again, should there be a little plus c there? Yes. Will it matter? No, because we're going to have another plus c on this side. We can just subtract it over whatever that constant was. We can just put over onto this side, and it'll all be a constant over on this side. So you only have to keep track of one thing at a time. But we know how to compute that integral. That's 3 times the integral of x dx minus the integral of 7 dx. That's x squared over 2, so this will be 3 halves x squared minus 7x plus c. So that's all of our solutions. That's all of them. We've solved the thing, right? So that's what it means when we say solve a differential equation. It means find all possible solutions. Here they all are. But what if I wanted just one solution? Maybe I have a real world problem where it's like, okay, all of these functions fit the differential equation that models my real world situation, but I need the one that models my specific situation. Maybe I'm doing a population growth model, and I know that the starting population is 500, but then my function gave me a plus c for starting population. How do we find the specific one? We narrow down to specific solutions by imposing what are known as initial conditions. To solve for capital C. So let's do an example. Let's solve f prime of x is equal to 3x squared, where f of 1 is equal to 2. Alright, so first, how do we solve these differential equations with initial conditions? And the answer is first you solve the differential equation in general, and then you apply the initial conditions to narrow down your exact solution. So in this case, f prime of x is 3x squared. So f of x, for the exact same reason as over here, is going to equal the integral of 3x squared dx, which is equal to 3 times 1/3 is 1. So this will just be x cubed plus c. Alright, so we have fx is equal to x cubed plus c. We don't know what c is, but we do have this initial condition. I know that f of 1 is equal to 2. But by my rule, for f of x right there, what is f of 1? It's going to be 1 cubed plus c. So 2 is equal to 1 plus c. Subtract 1 on both sides. That tells you that c is equal to 1. And now we have our final f of x, which I will write up here, just to save myself the space. F of x is going to equal x cubed plus 1. All of these are possible solutions to the differential equation, but the second we impose this initial condition, there is only one possible final solution to the problem, and that's nice. In general, a differential equation with n derivatives of f of x will require n initial conditions to give you a unique solution. So, what do we call that style problem? We call it an initial value problem, or a boundary value problem if you have the initial conditions at different places. But, yeah. Initial value problems are problems where we find a function that satisfies a differential equation, which I will abbreviate as diffeq, and one or more initial conditions. Alright, so let's do 2 more examples, and then we'll call it good. Let's solve for f of x if f prime of x is equal to 4x cubed minus 5x squared plus 9x, and f of 0 is equal to 3. Alright. Well, solve by integrating. We know that f of x must be an indefinite integral of f prime of x. So it will be the integral of 4x cubed minus 5x squared plus 9x dx, which is 4 times the integral of x cubed dx minus 5 times the integral of x squared dx plus 9 times the integral of x dx by the sum rule and scalar multiple rule. 4 times 1/4 x to the 4th is just x to the 4th. 5 times 1/3 x cubed, applying the power rule, is 5/3 x cubed. Integral of x will be x squared over 2, right, since that's an imaginary x to the first. So we'll have plus 9/2 x squared, and then it's all plus c. Okay, how do we get rid of the plus c? Let's apply our initial condition. We know that 3 is equal to f of 0, which is 0 to the 4th minus 5/3 times 0 cubed. So it's just 0 minus 0 plus, you guessed it, another 0 plus c. So c is already automatically equal to 3. That tells us that our final answer is f of x equal to x to the 4th minus 5/3 x cubed plus 9/2 x squared plus 3. Now, if you impose conditions that are not at 0, it doesn't necessarily mean it's just going to be equal to this. Even if you impose conditions at 0, it doesn't mean c will be equal to that thing, so don't try to make that connection. It's not true. But what is true is that you can always solve for c. Let's do one more differential equation. This one will be a little more complicated. But would make a very good test problem. Hint, hint, there will be a very similar one to this on the test. Let's solve for f of x if f double prime of x, so the second derivative of f of x, is equal to 0, f of 0 is equal to 1, and f prime of 0 is equal to 3. Okay, so I have a second order differential equation. I have 2 initial conditions. That'll be enough to give me a unique solution. How do we do this? I can't go straight from f double prime to f, because that's 2 derivatives, and the integrals are only going to do 1 at once. But I can go from f double prime to f prime. So, f prime of x is the integral of f double prime of x dx. That's the integral of 0 dx, which according to constant rule is 0x plus c. 0x plus c is just c. You can choose to do this one 2 ways. You can choose to do all the integrals at once and then apply your initial conditions, or you can choose to apply the initial condition. For instance, I could impose this initial condition now if I want, since I have f prime of x. Let's just go to the end and do it there. Get the general solution first. Okay, now we have f prime of x. We know how to get f of x from there. F of x is now the integral of f prime of x dx, aka the integral of c dx. C is just a constant. Any constant. Well, okay, what's the integral of a constant? It's that constant times x plus another constant. Maybe I don't want to call them both c since they might be different. So let's call this one capital D. So that's our general solution. And that makes sense, right? We have a linear function. I take a first derivative, that term drops, that becomes a constant. I take a second derivative, it goes to 0. So any linear function will satisfy this differential equation. But only one of them is going to satisfy these two initial conditions. We know that 1 is equal to f of 0. F of 0 is c times 0 plus d, which is just d. So d is equal to 1. And then we also know that 3 is equal to f prime of 0. F prime is just going to be c. We solved for that right here, actually. But you could just take the derivative here, and that will give you back f prime. F prime of 0 is 3, and that's c. So now we have c and d, which tells us f of x has to be 3x plus 1. So, again, more complicated differential equation. We had to take 2 steps because we had a second derivative instead of the first. But again, it's not, like, nothing crazy is going on here. We're just following the integral rules, and they're leading us to the correct thing. As long as you keep everything straight, it all works out nicely. That's kind of the good thing about integration. Alright, I'll see you all in the next video.